So, let's start the summer course, quantum computing. So it is the course about quantum computers and more precisely about quantum algorithms. But it is designed for mathematicians. Yes, so I expect your background not physics, not computer science. I expect the background of mathematics. And this would be the point of view from which I would subject. So organizational thing, there is a website. I will try to put all the presentations, some notes there. Yes, and it would appear there. Also, I created a group, which is very nice, especially for the case if I don't know, something has happened, the class is cancelled, or I'm late, or half of you are late. Yes, so then it's good to get notified. Yes, about this. And also there is my email also to write about it. Yes, and especially when it will be homework assignments. This is better. This is the best way of communication. So, you should learn music. So then we'll have to. I understand. Oh, I have a problem. Okay, now it works. So, what the course is about? Yes, it's about quantum computers, how they work. Yes, and I put here smile sign. And quantum computer is up to now is imaginary device. Yes, it still not completely exists. But it uses quantum mechanics. Yes, inside the course, but I will never refer to quantum mechanics. I will define certain mathematical model which will consist of quantum bits, which is analog of bits, quantum gates, which is analog of operations, and measurement, which is a very different from classical. And I will introduce it as a mathematical model. Yes, and actually, kind of you should how to say, think about the course is just presentation of this model and showing the scales to which it can be used. Basically, yes, it should not be considered as the last algorithm which was developed 1 year ago. Yes, I will present. I just show the limits. Why exactly the model changes? Because of quantum mechanics. But after I created the model, there is no need to know from where it came. Yes, this is becomes a question. At some moment, it would appear unitary operators. Why unitary operators? Because quantum mechanics. Yes. In classical computers, it was not unitary, here. Yes, and end of story. Yes. What mathematics will be needed? Yes, surprisingly very quite basic mathematics. First of all, complex numbers. But here I mean algebra. It's numbers, not analysis. It's numbers. So there is no poles, functions. So you need to multiply them to makes actually presentation, yes, for algebra. Second, and this is the main thing, it's linear algebra, finite dimension. Yes. But this we will use a lot, so consider this as the prerequisite. Yes, so we would consider bases, especially orthonormal bases, color products, linear operators, representation of linear operators, matrices, but only finite dimension. No need of Hilbert space, no need of Banach space, no functional interest. You can consider finite dimension space Hilbert space. Yes, so this is the correct way to do it. But there is a difference. Finite dimension. By the way, for me, it's not clear is it easier or difficult because we would consider finite dimension, but very high dimension. What is easier to study properties of linear operator space 2 to the power 100 or infinite dimension? For me, it's not clear. Yes. Important part that most of operators which we would consider would be self-adjoint or unitary. So those I suggest to rehearse. Yes, their properties. Yes, and also it's useful to know tensor products of linear space of finite dimensional linear space. It's not a prerequisite. I use it as a language, yes, and kind of tensor product theory, yes, is something that the language which I will use is not self-contradictory. Yes, okay, this is consistent. But I will define everything, I will use it as language. I will never formulate theories in terms of okay, why my notation is self-correct. Yes, so I refer to tensor products. Makes sense. Also, even that in the steel computer, there is bits, there are bits, so there are certain way of discretization. Actually, quantum computer, like language for classical computer is logic. Yes, we use
logic is 0, 1.
0, 1. Yes, I mean logic implications and or. Yes, and so this is combinatorics. This is discrete mathematics. Yes, and at the same time, the language for quantum computers is linear algebra. But even that it is linear algebra philosophically, it's much more related to mathematical analysis rather than to algebra by itself, in my opinion. Yes. And in particular, yes, in a lot of stories play a role for Fourier transform. Yes, but still, because this is computer, so we discrete Fourier transform, and okay, it appears not in the beginning of the course, in the middle of the course. So I will define everything necessary, but if you read yourself Wikipedia, what is discrete Fourier transform, it would be also useful. Yes.
I didn't quite understand about the fourth. About the tensor product. You will give the definition of the tensor product and everything.
No, I will not actually use tensor product as a this is a tensor product. Yeah. I will show some notation which I am using.
How it works.
And how I will present how it works. But for example, the theorem why if I calculate by 2 different ways why I would have the same result, okay, which is the tensor product spaces definition and so on, I will assume that.
So you will give some basic notation and examples.
Yes, I will give notation and examples. Yes. I will not formulate the tensor product easily. Okay. So because it's not necessary actually to understand. So it's necessary if you want to prove a theorem why this works, yes. But in the code, there would be quite a few things, not so many. Yes, it would be more like statements. Yes. And I very rarely show the proof, while sometimes I would. Yeah, so this is like not typical information because it's not definition, statement, proof. It's idea, calculation, example. Because it is still a computer, yes, so there are some prototypes, and I don't believe it's very good idea to make computer calculations in the blackboard, so it's good to run. So most of the course I will speak about so-called B-based quantum computers, or they're called universal quantum computers sometimes. And this is so because of this, I want also to introduce some platforms where you can run the code of quantum computers. Most of my courses, previous courses, I was using IBM Quantum Experience. But from year to year, they restrict access to that platform. You should pay. No, I mean, not how to say that's, and even more, it happens even from 1 week ago till now. Yes, so I still can use it to all purposes which I need. Yes, but I mean, this is a really dynamic story. So the first time I was doing this prototype of this box in 2018, and at that moment it was perfect. You can smoothly do everything. Yes, and like starting from 21, yes, it starts to make some difficulties on this one. Yes. So I still would use mostly the approach by having quantum experience, but there is a backup platforms. Yes, so the platform from Google, I never used it before. Well, things appears some difficulty at some moment. And there is much more minor project quantumcircuits.com. Yes, and because this is minor project, I don't expect any troubles with access to it. Yes, because they're still happy to have new users. Yes, so that I expect that actually quite a lot of things from this.
Yeah, what's probably a good question. If quantum computers don't exactly exist already, what do these platforms do?
So they have some quantum computers.
Okay, they have.
Yes. But
access.
yeah, you can access. So yes, on IBM you can now run. I don't remember how much. Say 10 minutes per month. Yes, of quantum computer time. More importantly, dramatically restricted to which computers you have access, which is actually more important than the time, because you will only run the things which works in milliseconds. Yes, so they're not perfectly working. So at the moment when we reach the first example of quantum program, and especially the best demonstration is for Grover algorithms. We will see how the theory is different from practice. Yes, so the kind of, and starting from I think 2020, we always have use. Oh, now quantum computer breakthrough, so they can solve a problem which were not possible to solve by classical computer. But still, quantum computers is not in our life, at least after public knowledge. Yes, so because there exist sometimes those breakthroughs, but they are not complete. Yes, and one of the lectures I will also devote to another model, which is a diabatic quantum, which are basically a good way to solve discrete optimization problems. And how to say there is a principal provider, it's debate on me, but for me, actually, this was the first connection. One people, but it now becomes more details. So most of the course would be based on two books. So Nielsen Chan is considered the classical for quantum computers. I personally prefer a book by Williams. Yes, but okay, both of them are, in the spirit of the course. And also some part of the course would be based on papers. So elementary gates, I will demonstrate, how something what is easy for classical computers can be not so easy for quantum computers. And the most complicated problem is solving of linear systems. And this is, okay, not line by line follow this paper, yes, but still it is. In the group in WhatsApp, I will upload all. So the model consists of three things: quantum bits, illusions. Today we will speak only about quantum bits. If the lecture will be shorter, then it will be shorter. So let's go. So I will define it step by step, from easy to more complicated. Yes. So what is one? Classical video is 0 or 1. Yes. And in quantum computers, there is their analogy, 0 and 1, and I will write it in such form. Yes, and please consider that if somewhere in the course we see such type of notation, this means this is a state of quantum system. Yes. So this is just, for you to see, yes, because one can be a number one, yes, or it can be a quantum state, yes. So if it is like this is a quantum state. So I will do everything very slow, yes, in order just to introduce notation as well, yes, right, to get used to the notation, yes. So, and this doesn't mean that phi is 0 or 1. Yes, it means that phi is a quantum state. And as famously Justin Trudeau told in his visitor to Canada Quantum Computing Center, so what is great about quantum computer, because it's 0 and 1 state at the same time, this is why I'm so excited quantum computer. So it's possible to have superposition of them. And now, without any explanation, the true explanation is quantum mechanics, I say the state of a quantum field is as such, like up to now I write it as a notation. So A0 times 0 plus A1 times 1, A0 and A1 are complex numbers. And I consider 0 and 1 as a basis vectors, certain linear space. This becomes just a vector in the two-dimensional complex space. So I define it. You can consider this in axial. Yes.
Does A1 absolute value of A1 plus absolute value of A1, A0 squares equals to 1?
Yes. So wait the end of this slide. Yes. So what has intuitive meaning is this. So intuitive meaning would be that is in a state 0 with probability A0 squared. And it is this in state 1 with probability absolute value of A1 square. Yes. What exactly does this mean? I will tell later in a section of measurements. Yes. But this is intuition which we should have for more. And because the total probability should be 1, yes, it is one condition. So, okay, not every one will be stable. Not every vector can be considered quantum stable. Yes, so it has to be satisfied this condition. Second thing is that also come from physics, and it could be less natural at this particular moment, is that each vector so is equivalent to complex number times itself. So if you multiply both A0 and A1 by the same complex number, the depth would be from point of view of physics, those two states would be undistinguished. So as a mathematics, there are two different vectors. Yes, but they are undistinguishable from physical point of view. Yes, so in a how to say third part of the course, yes, I will show another model which is density operators, operator density matrix, from which it would be clear why it is like this mathematically. Yeah, but up to now, this is just postulate. Yes, so they are considered to be equivalent. Yes, and because of the first condition, the C should have absolute. So the norm of which should be 1. So it is exponent of poorly imaginary exponent. Yes. So question. Yes. How many real numbers can describe the state of the quantum? The answer is actually 2, because we have the first A0, which is a complex number, so this is 2 real numbers. A1 is a complex number, so it's 2 real numbers, so we have 4. But we have one condition, one real condition, so -1, and one factorization, so -1. I mean, up to now, this is just calculation in figures. Yes, yes, but dimension of a quantum state is actually on a real space is actually 2. While given the whole course, I would consider this as a 2-dimensional complex space. The model would be by itself started such a way it would always respect this rule. So if I start with something which satisfies this, then I always get state with such vectors. And if I start with 2 vectors which are equivalent, then I would end up with 2 vectors which are equivalent.
Yes. So you could just use, like, if I just give you the magnitude of one, then you know the magnitude of the other. Okay? And then this is 2 numbers. It's not too difficult to believe it as well, right?
Yes. So even
if one magnitude, I can
like three slides later, I will even show the exact model how it can be represented. Up to now, I just I start basics, little to little, poco, step by step. So quantum statements. So the main thing that during the whole course, I would consider this as a vector in linear space. So I use this notation, and let us think for a moment that 0 is just a 2-dimensional vector, 1, 0. And 1 is 2-dimensional vector, 0, 1. Yes. In that case, this is basis. Yes, and then I write it as a vector, like how we usually manipulate these vectors. Yes, so nothing more. Yes. And so Then sometimes I will write like this. Be careful, yes, because I mean I created a certain confusion. Yes, because I told you two real numbers here, two complex numbers. I will always refer to complex numbers. Just I cannot, lie to you. Yes, I have to be honest. Yes. In fact, there is a certain dimension reduction. But I will always use this notation. So, what is better? We have classical bits or quantum. So, there are much more difference. There will be much more difference when it comes to multiple qubits. But there is a certain important difference which appears only on one, already on one. And this is a certain philosophical argument, which I would like to say. Yeah, because like what is the state of classical bit? 0, 1. It's very discrete, very little information. Quantum bit is two real numbers. Yes. It looks like this is much more rich space. It is one bit, you can encode a lot. But there is a price. And I think that exactly this price is why currently don't have quantum computer yet. Yes. And the price is that the state is continuous. It's not a discrete space. It's continuous space. And as soon as you have continuous space, the errors are not avoidable. Yes, you always have a little noise, you always have a little errors in your devices. Yes, so that's you always will have something not precise. And exactly this is the problem. So they are too noisy. And so that already now IBM provides even access to us to 100 qubits. And later we will see that 100 qubits in the perfect world is computationally more efficient than current computers. Yes, but they have errors. Yes, and those errors eliminate a lot of the advantages. Remember, yes, so when the classical computer starts, it was also a discussion because in the end they based on Kirchhoff rules. Yes, so it also was a discussion: should we encode like 0 or 1, or we should encode the real numbers, say the current near the rod. Yes, and because we know the discrete philosophy is. Yes. And maybe these no fast remembers, yes, but I personally remember when discrete photograph wins against analogous photographs. And so that's when the last time we used the long time, when we used the film, yes, when we used film, yes, the last time. I used it, yes. Yes, but in the end, as soon as it appears good technology for discrete, it completely removes the amount. So you should consider this as a disadvantage, the fact that it is not discrete. And okay, so I call it less curse pair. We have more information, this is less. But we have errors, this is curse, which we have different. There will be several other less curse pairs. So now let me explain why. Exactly why it is two real numbers. So I have original representation, and I can change it like this. Yes, and the reason is very simple. Because I always can write A0 in the form that this is absolute value of A0 times some exponent. Yes. And absolute value is a value between 0 and 1. So it's between 0 and 1. So I can represent it as a sentence. In the K, we will see later why for me it's more convenient to write this that not just that. As a data in that case it's from 0. Okay, yes. Now we can put this guy in front. Yes, and in that case we have a complex number. And we know that the absolute value of A1 squared plus absolute value of 0 squared is 1. Yes, so we can think that A1 is sines of A. Absolutely. And after this, we will also have factor of rotation. And in the end, because of gamma, nothing depends because they're equivalent. Yes, so then it would be described as yes, and okay, let us draw this from a sphere. Yes, and this is why I choose exactly such. Yes, so I consider the sphere from the vertical line. I would angle theta. Yes, it chooses me a circle on the sphere, and there I would rotate it by phi. Yes, and this is a point, would be a point on the sphere. And let me not explain all the details, but the sphere would create a proper topology. Yes, so what the states which are close to each other would close.
I'm still a bit confused because the first line you say is something in C2,
Yes.
C squared.
Yes.
And the second line, that just looks to me like a complex number. No, it just looks like it's.
Oh, sorry. I should put here 0 and here I should put 1. Oh, yes, this is a mistake.
Okay.
Thank you. Okay, so that's a mistake. So here it should be 0, and here it should be 1.
Okay.
Yes, so in that case it's a sphere. And this sphere is okay, as a sphere, it can be considered as a just play object. Yes, just play is the notion, to familiarize ourselves or to understand better. But first of all, it happened that this is a good visualization story. You will see most of the simulators, you can visualize it because the block sphere. And this is the block sphere. It's called block sphere. Block was the last name. Yes. And in my opinion, it's much more important when we come. So up to now, first 2/3 of the course, I will speak about perfect one. So the one which works without errors. What? Yes. And the third part of the course would be related to existence of errors. Yes, and in that case, block sphere would be placed by both poles. And there, in my opinion, it becomes quite a useful notion to demonstrate a lot of things which are not so obvious. So, block modes, yes. What? So this is block sphere.
Yes, and you said that
Block. When you come to calculations with noise,
Yes.
that you change with the notion state.
yes,
And in that case, it would be represented by both poles. Yes,
so does these things related to the block functions?
So I'm not expert in function. I wasn't so. It's fun. So let's play it. Where is the 0? Oh, let me copy from sine gamma was the zero plus sine 1. Where is zero? Where is the zero? Might be equal
So theta should be 0 and
what?
theta should be 0
That is zero.
and and gamma should be 1.
You don't have gamma here because it's
Okay.
Five.
phi is under gamma. Phi is not.
Yes,
Phi doesn't matter.
doesn't matter because
Yes.
once,
Because all the points with speed equal to zero is the North Pole. Yes. Where is one? So the answer is North Pole. Where is one?
so theta should be I pi should be 0.
Phi not matters. And here also phi not matters. That's not.
I think it's the south pole.
So this is south. Yes.
Okay.
And this is why people use the gloss here,
Ah.
because it accommodates all the how to say all the equivalence, all the topology space. Yes. Okay. Now I consider the seconds. It will also have a special notation. Yes, because it would quite often appears in the course. Yes. So this is half sum, but it's not really half, it's 1 over square root of 2 of 0 and 1. So I use this slide also to give examples of states, yes. And here, because sum of squares should be equal to 1, yes. So 1 square root of 2 squared is 1/2, 1 over square root of 2 squared is 1/2, total 1. So where is this point? What is this state? There was a question how it looks like assignment session. Yes, so I combined and I incorporated the lectures. So this is how it would look like.
I'm going to guess it's on the equator because that's kind of. But so I guess this Oliver's thesis pi.
So gamma is equal to, like, if you formally sum, as this, then first you will get gamma equal to 0. So there is no need to put it. Yes. What would be theta?
Yes. You want the cos, when the cos and sine are equal in the middle. I'm just trying to link cos and sine are equal in the middle. So it's pi over 4, so theta is pi over 2.
So theta is pi over 2. So it is somewhere on equator. That's pi over 2 corresponds to equator. What is pi?
Zero.
Zero. That's because the goal was to multiply on something, so to make perhaps right. A1 in form I5, that's absolutely A1%. And that is this form.
Yeah, it's sort of the rotation between the two different coefficients.
Yes. So, very good point. Yes, so this is kind of a relative angle of one to another. Yes. The force. And so I put instead of plus here, I put minus. What is here. So the first part is the same. Yes. Now we go to 0, here 3. But now what is
Say all the way around, which is plus,
Yes. Plus to the west.
to the west. So
No,
nine is the east.
Yes. A1 minus, I mean, okay, it would be minus 1 over square root of 2. Yes. The absolute value of A1 is 1 over square root of 2. And you need to make it in the form equal to 5 times 1 over square root of 2. Yes, so we need this to be minus 1. Yes, so 5 is equal to 5. This point. And the last, so I put 5 measurement. I equals to.
You have the same formula there. No. Yes. E exponential I5 1 over. Yeah.
5 will be yeah, the points. And
Now calculate the value of Rio de Janeiro.
so this is not arithmetic source, yes. So questions. Yes, if there would be a bit more theoretical, I will not discuss them. Plus today I would leave it for home and discuss next week. Yes. So assume that we have a state psi. Yes, it corresponds to some point close. Let me describe two other states, and I ask you where they are located on sphere. So first, later we see is that not of psi, is that we instead of A0, A1, write A1, A0. Yes, all zeros become ones and all ones become zeros. Yes, so this is not operation. Yes. 0 goes to 1, 1 goes to 0, but where would you set? Open. Please think at home. Yes. Can you provide a certain geometrical description? The second thing I would like to consider orthogonal state. Orthogonal state is such a state that its scalar product is original, yes, would be 0. Yes, so A0 B0 star plus A1 is 1. Star is conjugate. This conjugate is equal to 0. Note that this is two conditions. Yes, it's not one condition, it's two conditions because this is a complex number. So B0, B1 is something described by two real numbers. We have two conditions, so in general, we can expect that this is one state. Fine. And where it is on both states, you have general. So that's all is a 1 bit, 1 qubit. Yes. Now, And now let me come to multiple codes. And I will do in a form 1, 2, maybe. And then let me start with 2 codes. So the classical computer has 4 states 0, 0, 0, 1, 0, 1, 1. And I will assume that quantum computer also have 4 basis states. Yeah, so this is the way how I make analogy. Yeah, so each state of classical computer, each possible state becomes a basis vector in quantum. And all of them are linearly independent. This is my assumption. You can consider this as an axiom, as a proposition, as a construction, whatever. Yes. And quantum state, I will write as a vector. So in front of each basis vector, I will put a multiplier, a complex number. These the same conditions. Yes. Sum of squares, all of them, I 1, and 2 of them which are different. Okay, here I made some misprints. So 2 of them which are different by multiplication constant. So there should be silent here. Are undistinguished. So I'll just copy this from one qubit. And this is a proper way how you should scale. And why like this? Because of quantum mechanics. Yes, it's not a question to it's a question to go to those who pay. So, how many real numbers will represent state? Now let's question. What do you think? What? Yes.
6
Yes.
numbers.
Yes. The Zoom, I wanted to ask, might be someone from Zoom. And exactly at this moment it appears. Yes, it's 6. Why? Because each of the complex numbers are 2 real numbers. 8. We have 2 conditions, -1, -1. So 2 conditions. So 2 conditions in the end, 6 real numbers. And 6 is more than 2 plus 2 or 2 times 2. Yes? So this is more than just 2 independent qubits. Yes, so the quantum world gives you something richer than just two bits in the one system. Is richer than 2 independent bits. Yes, and now I would like to say what means to be independent. I mean, it's not a formal definition, and it also will be a good story. It also will be a good story for introducing tensor. So this is the first time in tensor product will show up. And even here it is not very interesting because 2 plus 2 is equal to 2 times 2. Yes, so the tensor product that doesn't give enrichments. Yes, but still it's a good notation. So if we have 2 independent states, so I will write them as a product of 2 states. Yes, and I open brackets and all the numbers, yes, I will multiply with each other. And those things I will write like formally one after another. Yes, and this is exactly the construction of tensor product. So the basis vector is a pair of basis vectors from each of them. Yes, and 0, 1 is different from 1, 0. Yes, and I use such a notation. So 0 state times 0 state is 1 0 0 state. Yes, and this is the way I'll write it. And now, yes.
So that's following the third line. So you take by definition the product 0 0 is your state 0.
Yes. Yes.
By definition.
This is kind of by definition. And this is exactly when you say, would you define tensor products? Yes. To make this definition not an example, but in general, yes, would be exactly defining tensor. Yes. And okay, so I know first is C00, the second C01, and so on. Yes, and so let me press attention. Yes, that here is a tensor multiplication. And the kind of the theory of tensor products tell you that, okay, I can write it as sum of 3 vectors. Yes, and open brackets as a sum of 3 vectors. Why in the end I always will get the same? Because of tensor products. Yes, so that's, you should trust me that, I can open brackets in my favorite way and always will get the same result. So if I have this state of 2 cubic system, which could be represented as a product, then the product of C00 and C11 is equal to C01, C10. This is 2 conditions. This is exactly this difference between 6 real variables, 2-qubit state for general bit state, and those who can be obtained from 2 independent bits. So this product, so this is 2 conditions. Yes, 6 minus 2 is equal to 4. Good math. Yes. So, example of state which cannot, it's clear that not necessarily this condition is satisfied. Yes, an example of such state is written here, so it contains only 0, 0, 1, 1. In that case, the right hand side is equal to 0, the left hand side is equal to 1/2.
I don't like this rules. How describe the independent state? As I understood that we can multiply anything.
Yes.
Or so.
So
what can you repeat what the definition of the independent states?
So I say, yes, that 2 qubits are independent. In the 2 qubit system, the state of 2 qubit system is equal to the product of those states in this form.
I see.
This is the kind of definition.
So the 2 qubit, so we have 2 independent states if the combined system, which is the 2 qubit system, can be presented as a product.
Yes.
So similar to the probability.
Yes, so kind of independent variables. Yes. So this is a bit more than independent variables because here the probabilities are complex, yes, not real, yes, but in the same spirit that they are independent as, so later we will see, yes, that kind of the measurement of the first qubit will not affect the second qubit. Yes, so this is the same, yes. So, tensor product is just a notation for this. Yes, so if I have this is phi, this is psi state, then this notation, yes, they are equivalent. So I write phi psi, this is this guy. This is the same as I write phi psi just in the one state. So phi epsilon not necessarily 0 or 1, they can be big numbers, a big story. Yes, and it's the same as tensor product of those vectors. And why I tell something like this? Because, okay, I told that 0 and 1, yes, state 0, 1 is basis. But you remember that usually if we are working linear algebra, I mean, nothing really depends on the choice of basis. We can choose other bases, yes? And we should get the same vectors in the end. And this is a hidden distinction, yes? So kind of when I write phi psi, I don't specify what is the basis. So here I specify what is the basis in certain sense. But it's not necessary. I can write still like this or like this, and still have the same vector in the end. Yes, so it doesn't depend which basis you choose. Yes, and so this is the correct way is actually not write like this, but to write like this. So, but because all products of vectors will be tensor products, or it will be scalar products, but for this I will introduce different notation for scalar products later. And because of this, I sometimes would omit. Yes. And the space is the tensor product. Yes, so get used that sometimes this appears, sometimes it doesn't appear. Such type of circle is tensor. Okay, multi-qubit state. And among all the definition of states, yes, 1, 2, many, this will be the shortest one. Because I would just immediately say that, okay, with analogy to 1 and 2 qubits, I will just introduce 2 to the power n possible sequences of 0 and 1. I denote each of the sequences a basis vector. I put complex coefficient in front of it and call that this is a state. And I will impose the same two conditions. Sum of the squares of absolute values is equal to 1, and the vector is equivalent to constant times itself. So here should be psi 1. So, yes, so that's there. So that's psi. That's psi would be c to the power 2 to the power n, because 2 to the power numbers here. I can write n tensor products of C2 is. Yes, I can say it in 5 minutes. Yes, well, but then I think a bit less intuition will be available. Yes, but so the rest would be some additional notational remarks. Yes, so that's not how to say materially, yes. But we need to get used to notation because we will use it during the closed course. So first of all, I mean, this notation is heavy, because it's long to write. It's very difficult. So I will write like this. Yes, I can identify sequence of 0 and 1 with a number. Yes, and I will write this number here. And A, which is a complex number, I will write as a coefficient here. This is notation. This is poor notation. So this is nothing more. So didn't introduce here anything. But this is much more useful. Yes, but the only thing that when I write G, in that case, I also need to remember somehow how many qubits there are. Yes, because if I write 3, then in case of 2 qubits, it is 1, 1. But in case of 3 qubits, it's 0, 1, 1. Yes, so that's so you should have context. Yes. So once again, this is the definition. How many real numbers one need to define to describe the state of quantum? That's correct. But can you be more precise? Maybe not you, might be some others. Exactly. 2 times 2 to the power n minus 2. Yes, because each complex number is 2 real numbers. There are 2 to the power n. Then there are 2. And what is important, and this is one of the power one, is that in n qubits, you have 2 to the power n real numbers. I mean, 2 minus 2, I mean, asymptotically. Yes, you have exponentially real numbers. So you have, in a certain sense, exponential memory. So if you want to encode 1,000 real numbers, it's enough to have 10 qubits. Basically, this is the philosophy. Yes, underlying. And we will see it in linear solution of linear systems, where we would observe the behavior. So if you have a big system, the time which you need to upload those numbers to quantum data is larger than solution of linear system. So you will solve with less time than you upload data. So this is philosophy, and actually the reason why short array works would be that we don't upload data for it. We create data for it inside. Yes, so yes, 2 to the power, 2 times 2 to the power n minus 2. Yes. I told that sometimes we need to know from context how many books then I write this here. And so this is the way how I write it. So if system, I divide system into 2 parts. Yes. And I can work with it like with linear spaces. So one of them I represent as a linear combination. I can write it after these open brackets. Yes, so all the rules to which we get used. Yes, just always remember that if you multiply, sequence of 0 and 1 times the next sequence of 0 and you concatenate. This is and this is what I will use sometimes. That's it. This is end of story. Yes. This is why we kind of formally I use them, but in practice, I mean, there is no need. Yes. Very important. So, if you have 2 equivalent states, yes, 2 equivalent states and 2 equivalent states, you cannot summate them because they have different coefficients in front of them. Yes, because I can write, yes, so that say 0 is equivalent to 0 and 1 is equivalent to minus 1. But it doesn't imply that 1 over square root of 2, 0 plus 1 is equivalent to 1 over square root of 2, 0 minus 1. I'm not sure that those so see, yes, but still. So never, ever, yes, never do like this. Yes, I put it in bold because This is not first time when I teach this course. And I mean, the first 5 lectures we will do easy calculations. But at some moment we start to do really messy calculations. And there would be a lot of willingness to, oh, okay, let me replace a state by equivalent. No. I actually suggest never use equivalent expressions. Because like formally you will always get, without it, you will always get the correct answer. Equivalence gives you not so much of profit, yes, because 2 to the power n, yes, this is there. And by equivalence, you can cut 1. Yes, wait, so not so many. But this is so much possibilities for mistake. Yes, so I suggest never ever, just never ever like this. Yes, so this is, let me stay on this slide more so you can see this, you will remember. Yes, so
Only like at the end of everything, then you can think,
yes, a kind of in the beginning or in the end. Yes,
For simplification.
yes.
So you can
But this is never used there. Yes, so okay.
inside the calculation.
Inside of calculations, yes, because you will make more mistakes that you will save time, yes, and the total time which you spend. Because if you make error in calculation, you have to repeat calculation, yes. So in the end, you will lose more time than you save. Yes, so that's never ever. Yes, and so sometimes, yes, for small number of vector, for small number of qubits, actually for 1, 2, 3. So example is for 3. So I can have this is 8 independent vectors. Yes, and I can write them down. Yes, and in that case, if I have a certain state, I can write it as a certain vector explicitly. Yes. And later I would consider operations with matrices. So I would potentially write matrices. I will never do this n bigger than for n equal to 4, it's 16, and I mean even this vector is long enough. So I think this is more a clear notation than this one. Yes, but still, I mean, because actually we would consider up to 3 qubits, we would consider certain basic operations. This, for them, I'm happy to write matrices. Yes, so I would sometimes. But I mean, never for any bigger than 3. So, how to remember how to make tensor? You write 5 psi, A, B, C, D. You write A times CD, B times CD. You get AC, AD, BC, BD. And this is just to remember the order. So,
This is not
what?
It is not
It's not commutative. So, but I mean, what means it's not commutative? If you think about it as a vectors from spaces, it's commutative. But if you think about it as a sequence of numbers, then it is not commutative.
I don't understand.
You should think that this space is not equal to this space. They are equivalent. It is still in a certain space. A, and this is in a certain space. B, yes, and AB is isomorphic to A. Yes, so that's only on the moment when you choose basis, they become non-commutative, because the basis is not. But as a vector, it is the same.
No, because if I change CDAD, I will get
As a vector, as a sequence of numbers, as a vector written in this form. But if you think about this as an abstract vector in abstract linear space, it doesn't
Yes.
matter.
Yes, you can change, yeah, you can.
Because kind of it tells that the space A tensor B is homeomorphic, yes, to B tensor A.
Monomorph or isomorph.
Isomorphic, linearly isomorphic.
So you have the unit.
You have unitary
Transform.
transformation, which ascends one to one. Yes, but if this is why actually it is not good idea to write in vectors, because at this moment the order styles play a role. Yes, so this. Okay, so today's class is shorter, which I think is normal for the first class. Yes. So today we think with quantum bits, in future quantum bits and quantum measurements. So a remark, yes. So usually the class will be hour and a half. Yes, not 2 hours. Yes, so I don't believe that for 2 hours people stress attention. Yes.
The some pause.
Yeah. So inside so they would be inside those 2 hours.
Yeah.
Yes, but we will start late and we'll have pause in the middle.
Yeah.
Yes, we'll finish earlier. So the Rio de Janeiro. Karaoke style. Yes. So, and I remember that I formulated 2 questions about block sphere. Yes, where they go. Yes. So there is you have opportunity, yes, to think about it. You can share with me your thoughts, your dubious doubts. Yes. Your excitement, yes, it's not forbidden to do, yes, and let me also finish with the first slide, so there was X necessary X. And I remember, so that I recall that now finish the class, stop recording, yes, and after this we will have a session in Portuguese for those who would like to have get in dúvidas depois ao class e português. Thank you very much.